All right, well, thank you, Bibosh, for putting this together. I've really learned a lot. So I don't know if you'll be able to learn much from me. I mean, I'm quite new to mobile health, and I'm relatively new to this whole idea of precision medicine, at least what I'm doing with it. But I have been thinking about functional data for a while. So I think that's sort of my, if I'm making a contribution, I think it'd be in that direction. So the title is kind of generic, just complex data, but what I really mean is functional data. And then, so as I go through the presentation today, I've given a previous version of this talk to some people who are familiar with functional data, but less familiar with treatment regimes and things like that. So I'm assuming this group knows the treatment regime stuff fairly well, much better than I do in any case. But maybe functional data is sort of a new idea to you. So I'll talk a little bit about how we can incorporate that into these other things that we're already doing. So, all right. Yeah, right up to the IT. Okay, I can just click. Okay, so this is my mHealth application, and so the idea is, so first of all, that's the logo, stress and activity study, and I hate the logo. I think that S looks kind of silly, but that's what they did is they gathered data from a lot of subjects, and it's. It piqued my interest because it had all this accelerometry data, and we had a whole talk about accelerometry data yesterday. And so you've at least been exposed to this a little bit. But the idea is understanding the link between stress and exercise patterns, or at least more broadly, movement patterns. And so the experiment is, and there's many aspects of this, and I'm just going to focus on one small aspect of it, but the experiment is measure people's movement for a long time, okay, with something like a Fitbit or something on their arm. And then after you've done that, then randomize the people. So half get a personalized model of stress, perception, and exercise. Okay, so that's a whole other project, right? How do you incorporate these two? But they teach this person about, this is how stress affects exercise, or exercise affects stress. Okay, so I don't think they're making any judgments which direction the arrow goes. Okay, and that's what half the people get. It's personalized to them, and then the other half get just something based on the entire aggregate database. Okay, so like, hey, here's the relationship between stress and movement. It's not specific to you, but this is what it is. So after the assignment, then they measure 6 months more of this movement. So it's a very rich data set. And then at the end, then they measure things like exercise behavior and health. And so the question then is, in this particular angle of this study is, if you present somebody with a personalized model, will that ultimately impact their health in a positive way? Okay, so that's what we want to do. So here's some daily actigraphy data. I think this is from children. Okay, and it's number of counts. So this has already been processed quite a bit. Okay, right? You get these X, Y, and Z directions, like at a very, very high fine time scale, and then it's boiled down to like number of movements, number of motions per 5-minute period or something like that. Okay, and so this is what it looks like. It's super noisy and hard to make anything of. Okay, this is the data. Now this is a different study. I think this is an elderly population, but it's actigraphy data averaged across days. And so now you can sort of see some patterns, right? At night, they're all asleep. They're not moving around much. Occasionally they might have to get up and go to the bathroom, or they might, move a little bit while they're asleep. Okay, but then at some point they wake up, their activity level goes up, and then it stays more or less constant until the evening when it slows down. Okay, so I see data like this, and I say, hey, that's functional data. Okay, there's lots of ways to look at this. There's lots of things you could measure, and then based on that, you could do your, your favorite precision medicine tool. But when I see this, I say, hey, this is a whole pattern, and I'd like to use the whole pattern in some way to help guide treatment decisions. And in this case, it is a very simple example, but the treatment decision will simply be, do we give the person the personalized treatment? Just present them with the model, or the general treatment. Okay, so are there some patterns at baseline that make a person more or less likely to improve based on getting a personalized model versus just an average model? Okay, and then can we identify a subgroup of patients, these aren't patients, but a subgroup of subjects that would benefit from this? Mm-hmm. Oh, so, yeah, this is many, many people. Yeah, and I think this is averaged over a week. Yeah, so I think it's week averages, many, many people. Okay, this I think is from the Baltimore longitudinal study, this particular plot. All right, so let me take a little side trip, talk about functional data. So anytime I see a function, I say that's functional data. We can use this in our models. And so if you see a growth curve, there's lots of ways to characterize this, right? You get some scalar summaries. But I say, that's functional data. Let's use it in the model as a functional data point. Anytime you see, something like this, okay, so you have children walk and you look at their knee angle as a function of time, I say that's functional data. And the red is the mean, for instance. You can look at the carotid artery, radius and curvature. Okay, this is just one subject, but think about doing this for many subjects. And then this is why I got into functional data in the first place. I'm interested in imaging data. Okay, so these images, as I presented them, it's a two-dimensional functional data. You can regard it as a surface, okay, and it's still kind of noisy. But the top three are all control subjects, and the bottom three are all depressed subjects. It's kind of hard to tell them apart, but wouldn't it be great to discover patterns in these that would allow you to discriminate between controls and depressed? So I'm not going to talk about that today, but that is like a functional data problem. So in general, if I were to give you a definition for functional data, I'd say, well, it's a curve, it's a spectrum, it's an image, it's a time series. Okay, it's anything that you can regard as being a function of some other variable. Okay, and it's often time, but it could be x and y coordinates or anything else, or spectrum. Okay, we'll see some spectra a little bit later. So, and that's a conceptual idea, right? I'm going to regard these as continuous functions, though in practice, I have them at a finite number of distinct points. Okay, so it looks like a vector. So right? If it's a vector, then isn't this just multivariate analysis all over again? Okay, well, the difference is there's structure in functional data. Okay, if you've got multivariate data and you've got BMI and you got age and you got genotype, and you can put those in any order. And as long as you do that same rearrangement with all patients, at the end you should get the same result out. But functional data have to stay in the same order. Okay, so that's sort of the whole point. And so a good functional data technique will exploit the structure of the data. Okay, so functional data, high dimensional, ultra high dimensional, oftentimes. And this is why I said complex in the title, okay, because there's a lot of it. And then one thing you have to do, this is one of the biggest tricks in a lot of functional data, particularly with imaging, is registration. Okay, and this will be an issue with this actigraphy data that I have. Okay, so you could have two people that have exactly the same activity patterns throughout the day, but one of them, wakes up an hour later and goes to bed an hour later. Okay, but it's exactly the same pattern. And so in order to make sense of that, we really have to register these things ahead of time. And sometimes it's the registration that's really of interest anyway. Okay, also smoothing. Functional data often comes with a lot of noise. Okay, and so related to this is dimensionality. So, we often have very high dimensions, like, thousands or tens of thousands or more, each one of these functional data object vectors. And so how do you deal with that practically? Well, we want to do some smoothness. When we fit these models, there's got to be some smoothness involved. And so we can project it onto some smooth basis function. We could penalize roughness. We could do both of these. or we could put it in a wavelet domain and do some thresholding, something like that. So I'll talk about the first two today. Okay, but that's sort of, depends on the application and what you're interested in. So what can you do with functional data? Well, this is what people have been doing for a while is, any statistical technique you have, that works for multivariate data, you can at least imagine a functional equivalent of it. So you can do functional box plots and discriminant analysis and, all this stuff. Okay, so I'm going to try to take a functional data approach to the idea of precision medicine with determining treatments, although in a very simple model. Okay, so here's sort of how you make the change from a linear model to a functional linear model. Okay, so if I have my functional data in a vector, I can just put them all together in a big matrix and say, well, this looks like linear regression. I've done this 100 times. And I've got a closed form expression for the parameter estimate, and off I go. However, if you've got very fine functional data, then your x transpose x will not be non-singular, and so you just can't do this. So, okay, fine, no surprise there. So we still want to get a beta here, but we have to restrict it in some way to where it'll give us a reasonable beta, and we'll still be able to compute it and interpret it, I would add. So this is another example from a while ago, but we might want to use imaging data and link that to depression symptoms. Okay, and so these are PET images, and then the idea is, well, I'm just going to fit a linear regression model. Okay, and so it's just like this is my outcome, and so this is depression score. The higher scores, the more depressed you are. I've got an intercept, and then I've got this inner product here, which I'll come back, and then I've got an error. Okay, so it's a univariate model. But the idea is I want to figure out some way to take the inner product between my functional data, in this case it's an image, and some other object. Okay, so the object actually has to live in the same space as the function for it to make any sense. Okay, and we'll look at an equation. But so, these things are all different, right? Every subject gets his own image, but this beta coefficient is now a beta coefficient image, so it's all the same. So I take the inner product of this with this, and then add something plus or minus, and then I fit the model. And so the big question is, well, how do I come up with this beta? How much smoothing do I have to do? Okay, so if you write it down in matrix form, it looks like this, and you say, okay, that looks like functional regression. But say, okay, well, practically, yeah, you got vectors and matrices, and you're doing your really standard stuff. But conceptually, I like to think of it in terms of the continuous functional data. Okay, so it's like the L2 inner product of X, your functional data, and then some beta function, okay, that has to live in the same L2 space. Okay, there's no reason it has to be L2 space, but that's pretty convenient in a lot of situations. Okay, so that's sort of functional data. Now from there we can go to functional linear regression. Okay, so I showed you an example a minute ago, but yeah, so this is that's the idea. You take this L2 inner product with your functional data and you predict some scalar outcome. And so people have been thinking about this for a while, and here's some examples. And I'll just show you an example with precision medicine in a little bit. But one thing I like about this, okay, so another approach you could take with this very complex, high dimensional functional data is just throw it in a support vector machine or something like that. And that's fine. You can probably get really good predictions that way. But oftentimes we're really interested in the interpretation. And so the point is, once I get this image, right, if it's an image beta or a functional beta, I can show it to my collaborator in whatever field they're in and say, hey, look, this is in the same space as your functional data. What do you make of this? And so in this case, this is how good the connections are along a particular track in the brain, and we're relating it to behavioral measures. Okay, so this is the estimated function. So it says, okay, if you're above the mean in the middle, then you're going to tend to be more positive than everything else. But if you're above the mean on either end, that's going to actually push your prediction down. Okay, so they look at this and they say, okay, it makes a difference if you're higher than average in the middle or on the ends. Okay. Okay, so now this is probably the stuff that you know really well. Talk about individualized treatment decisions or treatment regimes. Okay, and again, I'm considering the most simple case for now. Okay, we are making some progress since that on a more complicated case, but you only have to make one decision with these data. I really like this idea of continually making decision. I think it has lots and lots of application in psychiatry. I haven't been exposed to the data is all. Otherwise, yeah, I'd be really interested in that. So all we've got though is we got one decision to make. So it's not adaptive or anything, but hopefully whatever we do for this could be also applied in some of the adaptive regimes. Okay, so treatment is A, it's either -1 or 1. Okay, so what I've got as predictors is two types of variables. So one is just scalars, okay, and I'll call those things Z, there's P of those. And the other one is functional data. So I might have more than one function. Okay, so for instance, with the actigraphy data, I might have one profile for a weekday and then another profile for a weekend. Okay, because your activity patterns are probably different, weekdays versus weekends. Or, if you had enough data, you could split it. You have a Monday pattern and a Tuesday pattern. Some people go to the gym, Monday, Wednesday, Friday, something like that. Yeah, we're going to allow more than one functional data point. Okay, so potential outcomes, right? So there's how the patient would do if they got treatment 1 versus if they got treatment -1, but we only observe one of those. So a treatment regime is just a map. If you give me a bunch of Z's and you give me a bunch of X's, then I'll make a decision, -1 or 1, and that's specific to that subject. And how do you know if you're doing a good job? Well, often you just take the average across the population. Imagine applying your treatment regime to the entire population, and imagine computing this. And so, if yours is higher than mine, then yours is better. So we'd like to optimize that. Okay, so with functional data, that's kind of new in this. There's been a lot written about methodology for doing this kind of thing when you have scalar predictors. And I'd say most of it is focused on where you have just a handful of scalar predictors. There's much less regarding functional predictors. I put up there the only 4 references that I know, and 2 of them are from our group, and 1 of them is from my colleagues. So. Okay, so I'll start with the model, and then I'll describe 2 ways of fitting it, one sort of older and then one more updated. But the model is pretty general except an additive part. So I've got 2 pieces, and so the first one is the main effect, and then the second one is like an interaction effect, okay, because A is +1 or -1. And so this thing is only good for telling you, right, if you know X and Z, yeah, this treatment's going to tend to get better overall, okay, regardless of treatment or not. This one over here is what we're really interested in, right? Because if that's big, then it really matters whether they get treatment 1 or treatment -1. Okay, if it's close to 0, it doesn't matter which one they get. Okay, so that's a pretty general model. We're only going to look at a linear model here. Okay, so I've got my scalars here, and then this is my functional regression. I've got P of those. And that's the H function. And the F function, the interaction, I'll parameterize it the same way. So in order to fit this full model, I've got to estimate the alpha and the gamma, and then all of these functions. Okay, but, as we've seen, you don't always need to fit the whole model. Okay, you notice that this F is just the difference between how the patient would do on treatment 1 versus how they would do on treatment -1. And so ultimately, when you make the decision, the only thing you really care about is the sign of this F function. So, right, regardless of what H is, I can make the best decisions if I only know the F really well. Oh, so P is the number of scalar predictors, Q is the number of functional predictors. The other way around. Q scalars, P functional. Okay, so how do you fit the model? So this was our first attempt in this. Well, so we borrowed some tools from functional data. So project everything in terms of eigenfunctions, and then you penalize for roughness as you go. And then once you've done that, then you can just look at the coefficients of these eigenfunctions, and then just put those in any kind of treatment regime that works for low-dimensional data. At the time, we did this A-learning thing. And then, you have to choose some smoothing parameters. You can do it by REML. Okay, so this is our entry into this. Right, this is where we're first learning about this. But then later on, we decide, oftentimes we're going to have a lot of variables. And so I'd like to have some variable selection component to this as well. Okay, so this is one paper that I really admire. You guys probably know it pretty well, but this whole modified covariates idea, which is just so clever, right? It's based on this model, but if you take your y value and you multiply it by the treatment, 1 or -1, then you can drop that whole h out of the model altogether. You don't have to estimate it at all. And so that's modified responses or something. And then you can take the same thing and just rearrange it, and now you're modifying the covariates. It seems a little unnatural, multiplying your covariate by -1 or 1, but that's what you're doing. And so if you want to fit this model, don't worry about h at all. You can just estimate the f, and you can just fit this. And so that's half of the functional regressions I don't have to do, and half of the scalar regressions that I don't have to do. Okay, so that's sort of clever trick number 1. Now, as it turns out, that'll certainly work, but it's not necessarily the most efficient estimator you can get. So another cute trick from the same paper is, you can throw in this other piece, right? So for any function a here, because of the randomization, at least in my design, right? It's more complicated if you're doing observational data, but because of the randomization, that thing has expectation 0, and so I can throw that into my the function that I'm trying to optimize over, and it doesn't change anything asymptotically in terms of the estimates that I get, but it does change the variance. And so, I said, forget about estimating that main effect term. You don't need to do that. Well, it turns out if you can estimate it well, then you can get more efficient estimators by throwing that back in. So it's sort of a question of how well you think you might be able to estimate those. Okay, so this is augmentation. And you guys probably know this. Okay, so in order to fit this, so what we did is we sort of combined some techniques from a lot of different places and put them all together, and hopefully this will make some sense. Okay, but our loss function is the same as if we were fitting any regression model. So it's a squared error loss. But in order to fit this, right, I have this functional data that's too high dimensional. So I'll think about projecting that onto spline functions, and then I'll penalize their roughness. And so there's other ways to do this, but this is one that combines an L1 type penalty with a smoothness type penalty, and you can do this all at once. Okay, so this is the L1 piece, right? So this penalizes terms for just being in the model, and then this is the smoothness piece. And so, we write them out here. So there's, if it's 2-dimensional, it'd look like this. If it's 1-dimensional, it's just the squared second derivative. Okay, and then you've got the overall magnitude, which is also in there. Okay, so we'll fit the model with a penalty, right? So we're going to force some of these coefficients to 0. Okay, but now we want to, each functional predictor either has to, be predictive or not be predictive. Okay, I don't really want to say, well, the first half is not predictive, or actually that'll come automatically. But I want to do variable selection for the functional data as well. And so, before I go on, so 2 tuning parameters. One is for complexity of the model. So the bigger lambda gets, the fewer terms you're going to have selected. And then the other one is a penalty for smoothness. And you can think about having one of these for each one of your functional data points. Okay, but the bigger that is, the more it penalizes roughness, the more it enforces smoothness. Okay, but I'd like to take each functional predictor and either include the whole thing or exclude the whole thing. And so I can do that without having to do any extra work by making use of the group lasso. Okay, so each scalar coefficient or predictor is a group of size 1, and then each functional predictor is a group of size, whatever, how many spline coefficients I have. Okay, then I'll have to do tuning parameters, and so without thinking too hard about it, I can always do this just by cross-validation. Okay, so I'll just go really quickly through some simulated data and just kind of give you the main idea behind this. And this was not really to compare it against something else, but just to see, under what conditions is this going to work well, and under what conditions is this not going to work so well. And so we simulated this based on a psychiatry experiment that's also a randomized clinical trial. And we generated these things as if they're EEG data. Okay, so they have similar characteristics. And so, we tried like all possible combinations, right? So there's the contrast model. That's the F function that really makes the difference in choosing the right treatment. And so that could be correctly specified. In other words, it really is linear, or incorrectly specified. And then the interaction effect, that could be very large. The main effect and the interaction effect. They can be relatively small, relatively large, and all combinations of that. So spurious covariates, that's like junk. Okay, so variables that really don't help either predict or choose treatment. And so we have, a lot of junk variables that should all get zeroed out if my variable selection is doing well, and then other ones with very few junk coefficients. Okay, and then the functional coefficients with or without error, and then for a range of sample sizes. And then just to summarize then, the augmentation, okay, that's like estimating that main effect and then throwing that in there even though you don't need to. So that generally does help, particularly when the interaction model is misspecified. Okay, well, you tend to get more true positives with the model selection, but that's sort of balanced by more false positives. And then, you do much better with the treatment decision. Okay, you have more efficient estimators, so naturally you're going to get the treatments right more often. And then just as a sanity check, we said, okay, well, let's suppose we didn't know anything about functional data and just take these data and throw them in as if it was a vector and run the lasso and see what we get. So as it turns out, so we were expecting this to just be terrible, but much to our surprise, the treatment decision is not bad, okay, if you just forget about functional data, especially if you have large sample size. So it's doing the same sort of thing in a very crude way, but as far as choosing the treatments, it does all right. And so if all you're interested in doing is getting the treatment right, then you should maybe be doing a machine learning algorithm anyway. But in terms of interpretability, if you are also interested in that, then I think the functional data is a much better approach. That does better. Okay, so that's simulation, and now I would, yeah.
I was wondering if your credit model uses this relation, how are you specifying the relation between the x and y?
Between the,
assuming
oh.
you have this spline expression and then you have this
Yeah, so we dreamed up some coefficients for the scalar coefficients, and then we dreamed up some functions. I think it was on fitting this data that would be the true functional beta. Yeah. Okay, so that's simulation. So the next thing I would like to do is talk about the application of this data to the application of these methods to the actigraphy data. That is what I'd like to do next. Unfortunately, I don't have the data. So I asked Bibash, could we do this in April or May or something? And he said, yeah, no problem. He said, no, you had to. So I'm sorry. It's mHealth and everything, but I don't have the actigraphy data that I can actually show you an application to. So the data will come in, and it's not going to be quite so easy as I've got software, let me just run it through it. I mentioned the problem of registration, for instance. So we're going to have to go through that. Also aggregation, right? So is weekly, is that sort of a good measure to take? Weekly activity patterns, or should I average over, something more than that, right? You're trading off bias versus variance with that. There may be some outliers, and I mean, there may be not just outlying points, but like functional outliers, right? There might be some week that's really unusual. They're in the hospital, or they're on vacation or something. So there's going to be a lot of work to do. But anyway, so I haven't done that yet because I haven't had the data, but I can promise you when we get it, it's going to be awesome. Okay, so can we all get back together when we just okay. So what I'll show instead is an application to some psychiatry data, and this is actually the one that inspired the simulation. Okay, so you don't need to know all the details, but this is a depression study. Okay, it's a placebo versus sertraline, a standard treatment for depression. Not a huge sample size, about 60 or so of each one, but we have so this is the initial depression severity measure, and then sex, age, years of education. So we got 4 scalar predictors, and then we've got 6 functional predictors. And what these are, this is from this EEG study, they identified 4 specific, we've got them all, but they identified 6 specific electrodes that are thought to be predictive of how well a patient does to treatment. Okay? And I'd say, well, this is thought to be predictive of treatment, so it's thought to be part of the main effect. Okay, we don't really care so much about the main effect, but the thinking is if this is involved with getting better or not getting better, then maybe it's also involved with which treatment they should get. And so this is what it looks like. So this is a spectrum. Okay, so this is frequency along here, right? So you got low frequency over here, and you got high frequency, and everybody's got a different pattern. And each one of these lines is a different patient. Okay, and so for every patient, you've got these 6 functions. And then the response is how well you do at week 8. So in this case, it's actually backwards from what I've talked to before. The lower you do, the better, right? The better your symptoms are. This is multi-site. So, yeah, Columbia, Pittsburgh, I don't know, a bunch of sites.
And then score is also the same.
Yeah, that's pretty standard. I mean, there's different versions of it, but yeah, everybody was using the same one. All right. So that's the data, and then how did this work? Well, okay, so to check, right? And this is this is really just illustration. I don't want to make any big claims or big points on this, other than this is sort of how it works and what you get. But so we split the data, so there's 25 in the test data set, and then there's 107 in the training data set. So we got B-spline basis, we did 5-fold cross-validation, and what did we get? Okay, so this is what we got. So the model picked all 4 of these scalar predictors. Okay, so all 4 of these are thought to be useful in determining best treatment for each patient. And well, whatever. The coefficients are small, but this is, but still, significant. Now, as for the functional data, this function zeroed out everything except for these 2. Okay, so so these are all 0, these 4, and then this one is, it's the whole thing's negative, but it starts out higher and then ends up lower, and then this one has the same pattern, but a little bit less. Yeah. Oh no. Well, outcome is after 6 weeks, but yeah, the predictor is baseline. Yeah. All right. Yeah.
Maybe I missed it. So the coefficients for the functional data, they are linear.
Yeah.
The choice is based on the sample. How do you choose the degree of freedom in the functional coefficients?
Oh well, I mean, Well, so you can approximate it, right? I mean, by taking the diagonal of the hat matrix, whatever. But yeah, we use Dremel to do the smoothing within that. Although, you know, we use the regular cross-validation to choose those macro smoothing parameters.
So it's possible that these curves, these straight lines could be curvy. It's just your algorithm decided that they are.
Yeah, yeah. So if the truth is really curvy, then hopefully we'd get really curvy ones here. Mm-hmm. All right. So, you know, is this good or bad? Well, so to sort of, you know, figure out where we are, you know, relative to other things you can do. And again, this is just this one split. We actually repeated the split many times and got pretty similar results. So nothing's really astonishing, but still pretty similar. So let me show you what you're looking at here. So these are box plots, and these are the 25 in the held out test set. Okay, and so this is random assignment. So this is what actually happened in the trial. And then we had these different treatment policies. And so with the different treatment policies, you can only use the one that actually received the treatment that the policy would have assigned. And so this is the policy of giving everybody placebo. This is the policy of giving everybody the drug. This is what the outcome-weighted learning gives you, and then this is what we're doing. Okay, the modified covariates with the functional data. So the first thing you'll see is, wow, there's a lot of overlap there. So, I mean, even between giving everybody the drug versus giving everybody placebo, there's just not a huge difference. And in fact, with this whole data set, there's no significant difference there's no significant effect of treatment. Okay, just outright. And that's very common with depression, at least. There's a very small subset of people that it's really effective for, and it's just, you know, can we figure out who they are? Okay, so, you know, notice that this line is like way, way below those other lines. So clearly, right, this is the way to go, because it's, you know, look, it's so much. Okay, so, right, I don't want to make too much of a big deal of it, because it's really a tiny difference. And then if you look at the confidence interval, there's a huge amount of overlap. So I'm not going to claim anything on this. But we also said, okay, well, you know, what if we didn't know anything about functional data? So I already sort of tested that by just throwing it through the regular lasso and seeing what we get. But the other thing you would do, and this is what EEG people do all the time, they just, you know, average, maybe over just some frequency band or something. But they'll just take an average and then use that as a scalar covariate. So we did that as well, and that's actually kind of what our model gave us, right? Those two non-zero curves were pretty flat. Okay, so you know, maybe it's not terrible, but so we tried that using this modified covariates method, so with only scalars, and then also the same thing with CART. And the policy that they came up with is give everybody the drug. Okay, so it's, you know, so nobody should get the placebo according to that policy. Okay, so anyway, that's right. This is, again, not to prove anything, but that it works, right? And you know, depression's a tricky disease, and you know, I don't know if we expected a whole lot out of this, but so let me just make a few more comments then about where we'd like to go next. So in general, we're kind of interested in taking this high-dimensional data and then projecting it in some low-dimensional space, but choosing very carefully that projection so that the low-dimensional space is good for choosing treatments. And then we have done some work. I am not quite ready to present that yet, but with non-parametric link functions. So everything I've got is a linear model, and you know, that's certainly not true. And so we can then like do these projections, but then the link between the projection and ultimately the treatment decision rule can be non-parametrically defined and can be estimated. So we're doing that. It's not quite ready yet. Then going beyond that, I thought, well, you know, I've been thinking a lot about distances between functional data, or distances between more, you know, more abstract objects. And wouldn't it be cool if you could define a distance measure between images? I mean, sure, you could do like the usual Euclidean distance, but I think that'll be, you know, overly influenced by noise and might not tell you much. So maybe we can come up with some distance, and then And then when you have that, right, and then you have a training data set and you know who did well and who did not well, you just, you get a new patient and see who they're close to, and the people that they're close to, did they do well on treatment 1 or did they do well on treatment -1, and assign accordingly. And then other work that is almost done but not quite ready, and that is so more than 2 treatments. Okay, so this modified covariates paper, I really like this paper. It's so clever, but it really only works for 2 treatments, okay, -1 and 1. But it turns out if you constrain your model, and just additive, right, an H piece and an F piece only, if you constrain it to where the H is orthogonal to the F, then you can do the same trick and sort of get rid of the need to estimate the main effect. Okay, so you don't have to worry about if it's misspecified or not. So that's all I've got to say. Here's a few references, and I thank you for your attention. Oh, thank you.
I have a question. So, do you know of words or have you thought about, here you're treating about functional predictors,
Yeah.
standard outcome. Do you know of the word that deals with functional outcomes, but standard predictors?
Yeah, or even functional predictors. I've actually thought about this a fair amount, and I just kind of got stuck. Because with this same data, we actually have the trajectory over the 8 weeks, right? So we measure them several times over that. And so, yeah, you can boil that. I mean, like I was just saying, you shouldn't take a function and boil it down to a single scalar variable. But then, what do we do with these trajectories? Because, at some point we have to say, well, which treatment is better, this one or this one? Well, there's no natural ordering of these trajectories. And so, well, how do you do? Well, you could look at like the average slope, or you could look at like the endpoint or something, and then we're sort of back to square one. So yeah, functional regression problems with functional outputs are certainly out there, and there's a lot going on. I'm just not sure how to fit them into a framework like this. Like, how do you know which treatment is better just by looking at these functions? But yeah, that's exactly what we've been. I'm stuck, so if you have an idea, I'd love to hear it.
The last reference from you guys, and is that about functional?
No, that's just regular old group lasso.
Oh, so you're doing like group.
Yes, right. So we just group the functions coefficients together.
And then you also have some regularization.
Yeah. Yeah, right. We had the smoothness penalty and L2 penalty in addition to the L1. Yeah. Uh-huh. It's about the same for large N. Uh-huh. Yeah. Uh-huh.
And it turns out that with penalty, with some of the accuracies is better than function computation techniques. And I was thinking that it is possible to just regularize it, but the codes of the structure on it. For example, if you're going to do some preschool degree data, and eventually, if you are solving a L2 problem, you are going to involve the performance measures of the vectorized.
Yeah.
And then you can also assume some bandit structure from the performance measure.
Yeah.
I was thinking it's possible that you might get practically like this stuff.
Well, what you're describing sounds like another functional data technique, right? I mean, you are thinking about the structure. No, yeah, right. There are certainly people doing that, sort of penalizing directly rather than the spline coefficients like we did. Yeah.
We've had some discussion about like hypothesis testing, in like online decision making. I was wondering if I thought about hypothesis testing of like an entire function of your model. Is that easy to do?
Yeah, great question. Should this really be in the model or not? So I haven't thought deeply about it. There might be some permutation thing you could do, or alternatively work out the asymptotics and do it that way. But so I haven't done anything except thinking like, yeah, that would be something cool to look at someday. Oh,
we are running a little early, that's good, so that we can end early. Okay, so our next speaker is my colleague at NUS. He's an associate professor and now deputy head of the Department of Statistics, Professor Lee Jialian. We'll be talking about his work.
Oh. This one's definitely on.
Okay. Good afternoon, everyone. Okay, so I want to share with you guys one of my recent works on personalized medicine. Okay, this work is actually led by my PhD student Jin Li, and she is actually sitting over there. Okay, that's true. So this paper is about subgroup identification, and we try to use a statistical model, and under the model structure, we can have some sensible grouping characteristics. So this may help people doing better treatment. Okay, so this page of slides is mainly to motivate the idea of personalized medicine. Okay, for people who are not experts, I perhaps will spend 5 minutes talking about this. I think most people in this room are already quite familiar with this idea, so I will just be very quick. So, the idea here is we want to, nowadays, the treatment is getting more and more personalized, and we realize you just provide one kind of drug or one size of drug to everybody is not a good idea, and we should concentrate on specific groups of patients. If we want to provide specific treatments for those group of patients, then sometimes it may work better if you can identify those groups. So there are many factors that could play in this kind of work, and in recent, this kind of subgroup analysis or personalized medicine is becoming possible only because of the recent advancement in genomics, computational biology, medical imaging, and regenerative medicine. So this makes all this kind of applied research or targeted therapy more feasible. So once people are grouped into different subcategories, then you can provide more specific treatment to those guys. Okay, so here the idea is if you can't find the subgroups, then you are done. You have found the meaningful ways to do personalized medicine. But how do we? So here is a statistical question: how do we find the subgroups? Okay, so of course we need to identify the groups by using the information we have. Right, the information we have is just the data we collected in experiments or observational studies. So here we try to use a regression framework. So we would have response and we have outcome. We will have response with Y, which is our outcome we are interested in. And then we have a bunch of predictors, X1, X2, up to XP. So this is a usual regression setting. Okay, so now if you want to find out subgroups, then you can, these subgroups could form in different patterns. Then how should we find those subgroups, right? So this idea, of course, it should be based on the data you have. So here is one very hypothetical example just from our simulation study. It's one of our simulation setting. You see, in this picture, I showed you 4 scatter plots. Okay, the y-axis is the same. It's a response variable. And x-axis are 4 predictors, x1, x2, x3, and x4. Those 4 predictors are used to generate the response variable y. And we are designing the experiments, so we know who is from group 1, who is from group 2, and so on. Right? We have 3 groups in this simulation setup. Okay, so we know the subgroups for sure. And then you can tell from these graphs, some variables are more helpful to differentiate the groups than other variables, right? If you look at x1, then the 3 groups are just mixing around. You cannot really tell the difference of these 3 groups. x2 also is very hard to tell the difference. But like x3 and x4, it's perhaps much more clear on how to differentiate the different categories, different groups. So when we are choosing the subgroups, it's actually quite important to first select what kind of variable you use to divide the subjects into subgroups. So that's a important question we want to look at in this project. Okay, so before our work, there is actually an ocean of publications in this area. So there are already many papers published for this subgroup identification problem. Most of the earlier publications are related to decision tree. So they are also algorithms, all the subgroup identification methods are kind of like building a regression tree or classification tree. And you use a recursive partitioning algorithm and build different nodes. You get a different splits of your original sample and eventually end up with small groups. And those groups will be used for subgroups. Okay, so the earliest algorithm is called this AID, and then we have this THAID. So, and after that we have CART. You see, these are very ancient algorithms. And more recently, it's GUIDE. GUIDE is relatively most recent algorithm. But GUIDE is also just another regression tree, but it's just to use local polynomial for the different regions. Okay, it's also related to regression tree. And also this model-based recursive partitioning, it's also based on tree. And the interaction tree, it's also tree methods. And sites methods and VT methods, those two are the most recent one. They were developed like in 2016 or 2017, so very recent. So all these works, they have very good performance in practice. Many of them are already applied in clinical trials, in clinical studies, and they have received a lot of attention already. And all these works has been published and has been used. So just the thing is, so we just actually to tell you guys, it's like 1 or 2 years ago, exactly in this room, in this lecture hall, actually most of the developers of these methods, they are actually sitting in this room exactly. They are having a workshop on personalized medicine. So I was fortunate to be able to hear what they are talking about. And then I realized it's a very interesting area. And then I also realized what I was doing right then was actually quite related to them, even though I was developing some kind of very theoretical statistical models. But then I realized it can actually also be applied for this purpose, for this personalized medicine. So that's when I asked my student to start developing the following works. And it's built from the earlier works, and all those earlier works, they are already brilliant. Okay. So our work is slightly different from those earlier works because we try to use change point methods. And in this kind of change point framework, it's actually not new to statisticians, but most of the time, change point has been used in economics. Okay, for time series analysis, people use change point detection methods all the time. Okay, so they try to find the year difference, try to find where there is a financial cycle, where there is important breaking structure. So from the time series, so that's a long-standing problem in statistics, and many people have contributed in that area. But what we are doing here is try to use this change point framework into a regression setting. And then under this regression setting, we can form subgroups very naturally. Okay, so then you need to realize in this area, in this change point estimation area, usually there are two steps, two important questions we need to answer. Okay, the first question is we want to decide the total number of change points. Okay, that number is not a Euclidean parameter. It has to be decided, it has to be estimated, but this quantity is just a number. Okay, so the estimation for this number is usually very hard. If there is only one change point, then that's very easy. Okay, you just need to answer the second question. The second question is you find the location of the change points accurately. Okay, but if you don't know how many change points are there, then that's actually a tougher question. You need to first find out their locations first. Okay, so these two questions must be answered. Okay, so even for the change point literature, there are many important methods that have been proposed in the literature. One type of methods that is very popular is the cumulative sum methods. It's also some kind of binary segmentation method. It's used some kind of iterative cumulative sums to do, just keep dividing the interval into two parts and then do the splitting repeatedly. This kind of method is very accurate from what's reported in the literature. It's very accurate, but they tend to be time consuming. Okay, so the recent authors try to use a penalization method so that it can improve the calculation speed. So that's also what we are going to adopt here. We're also using penalty methods. Okay. So in this paper, we are actually more interested in finding the thresholding variable. So using what variable to split a sample is actually more important in this project because other pieces has been well constructed already. So we are just borrowing existing approaches into this project. So those things are not new. But what's new here is we care about the thresholding variable. We want to find out appropriate variable to use to split a sample. You see, for example, in economics, if you do time series analysis, the splitting variable, the thresholding variable is just a time. Okay, you just look at whether the time is below 1995 or after 1995. So time is a variable you use to split the sample. So you separate the time series into two parts by looking at the time. So that's very natural. Okay, but in medical studies, in clinical studies, we have so many variables, not just time. Okay, you can use age, you can use a person's age, you can use body heights, body weights, or other genetic information, right? So everything you collected can be used as a thresholding variable. So here we want to extend the earlier works so that we can incorporate more important variables into this thresholding variable. So this is kind of similar to the tree methods where you have to decide the splitting variable. So in the tree method, you also need to consider for what variable you do the splitting. Okay, there is some similarity in that sense. All right, so now let me introduce the model we are trying to study, okay, in this project. It's just very simple regression model. It's a very simple linear regression model. Basically, it's just a piecewise linear model. In this piecewise linear model, you can see, okay, depending on the value of z, okay, depending on the value of z, the regression coefficients for x will be different. So this beta is not a constant for all the groups. So beta has a subscript j here. This j depends on the change point. Okay, depending on which change point you are talking about, then this beta j will be different. So A1, A2 up to AS plus 1, those are the change points for Z. So in this model framework, it's kind of, we are looking at the spectrum of this Z variable. We look at the range of the Z variables. A1 is the smallest change point, A2 is the second one, and A3 is the next one. So we have this kind of change points. And these change points divide the region of Z into totally S regions. And so in these S regions, we will have different regression coefficients, basically. You see, if I tell you the change point, if A are all given, if A are all known, then this problem is very simple. You can solve this problem just using undergraduate linear algebra. Okay, just a linear regression analysis. It's just a piecewise linear model. But the non-trivial part is that the change points are unknown. And even more difficult is that this S is also unknown. You don't really know how many subgroups you have. You don't really know how many change points you have. So we needed to estimate the regression coefficient beta. So that's a regular parameter. So that's a parameter we usually care about. But in addition to that parameter, we also need to estimate the location, A, and also estimate how many A you need to decide. So this is a model we are going to care about. So in the previous work, so this is not a new model, actually. In the previous, one of my previous theoretical work, we have studied this model very rigorously already. So in that model, in that paper, we developed a two-stage multiple change point detection methods for this model. And we are able to estimate the number of change points with a strong consistency. So the number of change points can be estimated almost surely. And the locations can also be estimated almost surely. Question? Oh, sorry. Yeah, exactly. I forgot. So I was going to the mathematics too quickly. So perhaps here I need to declare, right, this model is actually quite general. It can incorporate both prognostic and predictive signatures in this kind of framework. So if you have a treatment, you can actually just imagine treatment is one of the X variables. Okay, so it can be applied in this way. So so usually for treatment selection, for treatment recommendation, when you are recommending different treatment, is because the reason is because you are thinking the treatment effects are different for these different groups. Okay, so this X variable could actually incorporate all kinds of treatment variables. Okay, but in addition to treatment variable, X can also include the prognostic factors. So many other things could be included in these X variables.
Are the Z's observed?
That's a good question. Yeah. So in the previous models, we assume Z as observed. But in this project, we also assume the data are observed, but Z has to be constructed from the observed data.
Z is a function of the X.
That's right. Yeah. That's a new development here. That's a only new thing, actually. That's right. That's what I'm telling you how to construct the Z later. Yeah. You can do that. I think this X can also include interaction term as well. Yeah. So it's not limited to any types of vectors of variables you want to consider. So any predictor variable, you can put it inside. And we can also allow some of the variable to be varying over the subgroups. Some can remain constant. So we can allow high dimension also. We can allow sparsity as well. So in our original work, it's a theoretical paper. So it's actually can cover all kinds of situations. Okay, so we can estimate. So we are assured that the number of change points can be estimated, and the location of change points can also be estimated. Okay, don't worry about that. And most importantly, the regression parameters can also be estimated consistently, and they enjoy the oracle property. The oracle property means, okay, if you know the true value of A, J's, and S, and in that situation you apply least square, that kind of estimator is called an oracle estimator. So for that kind of oracle estimator, we know it's just a least square estimator, so it has all the asymptotic normality, it has all the nice properties, and it's very good under our principle, under our methods. Our methods, I will also tell some details later. Under our methods, we can also find out the coefficients, just like we know the locations. So it's quite a general framework. And also in Li and Jin, in this paper, we can allow the response variable to be censored survival time variable. So in that case, this linear regression model just becomes the accelerated failure time model. Okay. Although the proof, the argument is slightly more complicated, you have to use some counting process language to show the consistency. But we can indeed do that. So in terms of implementation and theoretical argument, there's already no problem with this model. Okay, so just to be simple, what are the two stages for this estimation problem? So these two stages, including the first stage of splitting the observations into multiple groups. So at that stage, we're actually doing some kind of penalization. We try to assume there are Qn that many subgroups. You can let this Qn is kind of like a tuning parameter. You can let the Qn to be very, very large. And then, okay, for each piece, for each segment, so you have Qn that many segments. For each segment, you can estimate one regression coefficient change. That change is like the jump at the change point. Okay, so we basically just penalize the jump. If the jump is penalized to be 0, then we would declare there's no change point at that point. Otherwise, if it's not a 0, if the jump is not a 0, then we would identify one change point at that particular location. So we just do this penalization idea in the first stage. But this stage, the results may not be very accurate, even though it's kind of, it will lead us to the very, very close to the truth, but it's still not very accurate. So we have one additional step called a refining step. So the second step is even more complicated. It just involves the cumulative sum methods again, the binary segmentation methods again. But this method, as I told you earlier, it's usually very time consuming. But because we have the first stage we use the penalization methods, so that method is very fast. So because of we have the first stage, we can do the second stage more efficiently. So, so after the second stage, we refine the number of change points and all the analysis results. We can actually achieve the estimation results much better. So these are the basic ideas of this two-step multiple change point detection methods. Okay, now here, to address the question just from the audience, here we have this z variable. This z variable is our thresholding variable. So normally, in many situations, okay, we can assume this z is given. So just like in the previous work, we assume z is given. However, okay, if you in practice, okay, the choice of this variable could be very important, and how you choose this variable will actually lead to how you interpret or identification of the final subgroups, and those subgroups will be defined according to this z variable. So if you don't choose this z variable wisely, okay, you may end up with very poor subgroups. So we have to think about how to select this z variable more appropriately. So in this paper, we don't have any proof. We don't have any theoretical results. We only suggest a few practical ways to construct the thresholding variable. The first approach is just to choose one of the covariates to be the thresholding variable. That's kind of like the regression tree methods. Regression tree method is also selecting one of the existing covariates to be the splitting variable. Okay, so you do this, and you can use some kind of optimality criteria and see which covariate can give you the best result. So in this method, the thresholding variable z is just one of those x variables. You can use x1 or x2 or others. So that's the first method. The drawback of this method is just this z variable only contains information from a single covariate. So it might miss information from other variables. Okay, so the second method we introduce here is to consider a weighted average of all the covariates. So this way you can combine all the x variables together. Okay, you can have all information from all the subjects, from all the variables. Okay, so in the second method, if you don't have any prior experience, if you don't have any prior information, you can treat all the x variables equally well. So you can actually just use average. You can just use W to be equal weight. So that's actually what we are going to use for this second method. So we consider equal weights for all the variables you want to consider. So this second variable is slightly better than the first one, since now you can combine more information to be used for the underlying variable. Okay, but equal weight may still not be a good idea, because these x variables, clearly some of them may be more important and some of them may be less important. So they could, you should have some kind of favoring over them. So the third method we consider is actually very simple. We consider the multivariate analysis. When we think about multivariate analysis, we realize there is a very classical approach called the factor analysis. And this factor analysis basically is operating on the design matrix X. Okay, for this design matrix X, you can do this kind of multivariate orthogonal decomposition, and you can decompose this original X variable into many factors. Okay, these F quantities are called factors. So if you I believe this is usually covered in undergraduate curriculum already. So it's quite a classical approach. We also have R also have software function that can do the factor analysis automatically. So it's very straightforward. So the nice thing about the factor analysis here is, after you do the factor analysis, the original matrix X involves P predictors. Okay, all the predictors are included in this original matrix. It's p-dimensional, but each one of this F. So this F is usually of a much smaller dimension, and so usually the first factor and the second factor, they are usually like the most important ones, and the other factors. So if you sort them according to the eigenvalues, so the first few factors usually they are more important. And so here, our third recommendation is we recommend you choose the thresholding variable to be the factors, to be these latent factors. Okay, so these latent factors are directly extracted from the original data, from the original X variable. So these factors, depending on the loading, they actually will actually assign different weights to the different variables already. So each factor is already constructed based on a linear combination of X, but the weight is constructed based on the factor analysis. Okay, so it's a very automatic procedure. And those weights automatically incorporate the consideration of like the variance, like the information of your data sets. So it's a very simple idea. And so in here, we can do the factor analysis to X very easily. And I just want to briefly mention that in practice, you see, this is actually recommended by a referee when our paper was reviewed. The referee actually said, when you do the factor analysis, so you put all the X variables into this matrix to do the factor analysis. why don't you also put a y into this X matrices? Okay, you just include a y into these matrices, and then you do factor analysis again and choose that factor. And that factor might be more relevant to y, right? So you think this is maybe a good idea. And operationally, there is no difficulty doing that. I can do that. I can do that kind of computation. But the problem is, if you look at our model, the factor, if you choose the factor in this way, so now your z will be our factor. And this factor is constructed not only from x, it's also constructed from y. So y will appear on left-hand side and also right-hand side. Okay, if we insist using a statistical model, then I would not allow y to be on the right-hand side. Otherwise, it's very hard to interpret this model. This model is not interpretable. So I actually didn't follow the reference advice for this paper. Okay, of course, operationally in the future, if you just want to do subgroup analysis, if you don't care about model, then it's okay. You can definitely do factor analysis using y in this sense. Okay, it could be some kind of supervised learning, right? There's some kind of supervised machine learning approach in that, defined in that way. Okay. The fourth method, of course, since you can use factor analysis, you can also use PCA. So principal component analysis is slightly different from factor analysis. I think factor analysis is care more about the orthogonal relationship between those factors, and the PCA is caring more about variance. It's also decomposing the original design matrix X. So the X variable is decomposed into multiple principal components. And here, the first principal component, usually it maximizes the variance of all the linear combination of these X variables. Yeah, so that's the first that's the first principal component. The second component also maximize all the linear combination of X, conditional on that the second principal component is orthogonal to the first principal component. So you sequentially solve this kind of maximization problem, and then you end up with a PC1, PC2, and PC so on. Okay. So this PCR, they are also orthogonal. So PCs are different from factor, but they can also be regarded as a linear combination, also kind of like a linear combination of all the X variables. And it's also very easy to construct. In R, you can also use existing software to compute all the PCs. And we would recommend you use the first PC to be the thresholding variable, because the first PC contains the most information. It captures the most variance. So comparing method 3 and method 4, the strength of method 4 is it can actually be extended to high dimension. You see, for method 3, it's a traditional factor analysis. It can only be used for n bigger than p. Okay, but for PC, for principal component analysis, you can actually do high dimensional data. You can apply that to high dimensional data, even if your n is smaller than p. PC can still work. Okay, in that case, you can do the singular value decomposition. That's a special type of PCA. So in R, it also has this SVD function you can use so that you can find out the thresholding variables. Okay, so those are the 4 recommendations we make to find out the thresholding variables. And after you have the thresholding variable, you can then go ahead and fit this regression model again and get the estimated subgroups. Okay, so that's the basic idea. Now I want to show you a few simulation results. So in this first set of simulation results, we assume data are generated. Okay, so the data are generated from a regression model, but most crucially, we want to make sure that X variables, they indeed follow some kind of factor structure. So when we generate predictors, we also generate predictors from some kind of factor model. So this is a very popular vector model where people usually use to generate the data. So you have some kind of underlying factors F, which follow some kind of multivariate normal distribution. Yeah, they are IID. And then you use F to construct X. And then from X, yeah, X is just another linear combination based on normal distribution. And then based on X, we can consider different scenario to generate Y. So in case one, we consider generate Y from X using this one equation. In this equation, we don't have any subgroup. So this is actually important. In all the subgroup analysis problem, in all the subgroup identification problem, it's most important that you must protect your type 1 error. Okay, you cannot, because in this kind of calculation, it's very easy to get a false positive. Okay, if you don't have if you don't have subgroup and you declare there is a subgroup, then that's called a type 1 error. Just like in hypothesis test, you have some kind of false positive. So that's why usually we have to check. Okay, we have to make sure when there is no subgroup, our method should still work well. Okay, otherwise you bring some kind of false positive to the procedure. So that's the first case. In the second case, we consider two subgroups. So in this case, we use F. We use in the true model, the splitting factor is the first factor we used to generate X. Okay, so this true model follows this pattern. The two groups are actually defined according to this F. And since here we have 4 predictors, so from F we actually generated 4 X variables. So in these graphs, I showed you the scatter plots of Y against these 4 predictors. And you can already see that for some variables, it seems for X3 and X4, these two groups are separated quite well. And in case 3 is slightly more complicated. So that's what I showed you at the beginning of today's lecture, today's talk. Okay, in this case, we have 3 groups. And these 3 groups are also defined according to F, the first factor. And we have 2 change points here, so that we have 3 groups. Okay, the third method is when we have some kind of binomial, a Bernoulli random variable U here. This U is kind of like a treatment variable. So that in this case, we are actually simulating example that is similar to clinical study, a clinical trial, where you have treatment selection. So for treatment variable, it's usually a binary variable. So this U is generated from binary data. And still it's like there are 2 groups in this scenario. Okay, so those are the data generating mechanism for our simulation. So I didn't show you all the simulation results. I just selected one piece where sample size is total is 300. Okay, for the first case, in the first case we have no subgroup. Okay, in that case, the number of change points should be 0. There shouldn't be any change point. So if you look at this column, the last column, this is where we report how many subgroups you identified in average. Okay, so we compared with many methods in the literature. So AIM method, SIGBT method, PRIM method, and MOB methods, those are all existing methods in the literature. They have R package as well, so we just use their R functions. And then this F1, F2, TSM, CD are our methods, our proposed methods. So what's the difference between F1 and F2? Do you remember? Oh, yeah. Thanks for reminding. Okay, there are two estimation methods for factor. So in R, one method is based on a maximum likelihood estimation. Another method is called the Thompson method. So there are 2 methods. One is more unbiased than the others. Okay, so F1 and F2 stands for these 2 estimation methods. Okay, so those are our methods. And ALM methods is just assume linear model. You don't do any subgroup analysis. So it seems for the first case, there shouldn't be any subgroups. The truth should be 1. Okay, the truth should be 1. So indeed, our methods identify there is no subgroups. Okay, pretty close. And MLB is also quite okay. It only slightly larger than 1. But the other methods, it seems they insist there are 2 groups. So the other methods are all wrong. Even when there is no subgroup, they still try to split the data into 2 groups. Okay, so those are the number of change points. And then the first 2 columns are the mean square error for the training sample and for the test sample respectively. And you can see in this case, LM is actually the oracle method because the true model follows the linear regression model. So linear regression model indeed perform the best in terms of MSE. Actually, not necessary. So for training sample, it seems some machine learning methods, they are much better. They have much better training sample error. But for test sample error, they are worse. Those methods are worse because they incorrectly split the data into different groups. And for test sample, our methods and linear model methods are pretty close. We are all we have much smaller MSE. So this is case 1. And case 2, case 3, and case 4, we all have subgroups. And you can see the true groups numbers and our estimated group numbers are pretty close. And also in terms of mean square error, our methods also always perform next best than others. So using our factor models, okay, our methods can indeed do quite well. So we also have other simulation studies. So, and we have checked many other scenarios as well. And the observations are kind of similar. So let's move to the final example. Okay, so the example is from Wenke. So Wenke is my longtime collaborator from UCLA, and he has this kind of very wonderful data set from a scleroderma trial, which he was involved in that clinical trial. And so in this trial, the response variable is this MRSS score. This is kind of a measurement for the patient, which measures the severity of the disease. This is a primary outcome variable. And we have a few predictors in this data set, including disease progression, index of pain, health assessment questionnaire, patient self-assessment of disease progression, non-performance, and age. So all these variables are used as our predictors. So in this case, we will do analysis based on this data. So I think this is our estimated results. We use the different types of methods, and eventually our factor-based methods, in average, we have we actually did a random simulation, and we repeated we do the training and test sample. This way, we do it separately. We do the cross-validation so that we have training sample and test sample. And when we check the performance of MSE resulted from using this different subgroup analysis. Because so in this project, what the criteria is actually based on prediction. Based on if you have a better, so we believe if you have a better subgroup structure, if your structure is better, then you can actually predict the outcome better. Okay, so in that case, MSE should be smaller. So that's something we want to look at in this case. Because we don't really know how many subgroups there are. So this S is really, we don't know. It's just based on different methods. It can give us different different number of groups. But indeed, who is better, who is worse, we perhaps have to look at MSE. So in this case, we find out the factor model-based change point method is actually provides us like the smaller MSE. Actually, linear model is not that bad. Even linear model is quite good in this case. This is the first example. Okay, in the second example is a high-dimensional data. In this case, we have gene expression data from 24,000 genes. So those are the predictors. And then we have only 97 subjects. It's a very small data set. It's a very small number of subjects, but the data set is large. Okay, we have many predictors. Okay, so in order to analyze this data, we consider several approaches. In the first approach, we try to do some kind of bootstrap. Each time, because our procedure, we cannot afford to do calculation for 24,000 genes in our algorithm. I don't think any of the algorithm can incorporate that many genes, that many predictors. So what we did here is we do this kind of bootstrap. We bootstrap 500 times. Every time we randomly pick only 20 genes to fit the model. So that's what we do. So we pick 20 genes every time, and then we try all these different methods. And each time with these 20 genes, we can do the subgroup analysis. We can do the subgroup identification by using existing methods and our methods. And we repeat this 500 times, and then we look at the average performance. So in this way, we hope that this 500 bootstrap, of course, you can do much longer time. Bootstrap is affordable. We can make this longer, but here we only report results from 500 times. Okay, hopefully this 500 bootstrap can cover this 24,000 genes, all of them. Okay, so each time we have 20. So if you look at these results, we can see that in terms of number of subgroups, we actually have, we could end up with quite a different number of results. If you use existing methods, the number of subgroups is only 2. And using only a single, so one TSMCD, this is the method we introduced today as the first method. And a TSMCD method is our second method where we take equal weights to all the variables. And F1, F2 are the third methods where we use factor analysis to find the thresholding variable. And PC TSMCD is the fourth method where we consider principal components. So those are our proposed methods. And you can see our proposed methods usually can recommend more subgroups than the existing methods. Indicate we tend to be more sensitive in detecting the number of subgroups. And in terms of accuracy, also it seems the factor-based methods has like the lowest, or actually PC has the lowest MSE, the smallest mean square error. So in terms of accuracy, our proposed method is also performing quite well. And this last column reports the average time you spend to fit each model to get the subgroups. Okay, so in this case, linear model. Anyway, so this is the first analysis. In the second analysis, we choose 20 genes. This is actually a very old data set. This is a publicly available data set. So it has been analyzed by many earlier authors already. So we just use 20 genes selected by other authors. So just use those genes as our predictors. And in this analysis, we use the results from my colleague's paper, Yu Tao's paper in 2011. Okay, in that paper, we select 20 genes based on ROC analysis. And then we repeat the same calculation for all the methods. And still, it seems our methods perform quite well among all the results. It seems our methods tend to have smaller MSE. The last method is also based on the earlier authors' results, where in this 2016 paper, they identified 4 markers from this data set. And so we use those 4 markers to construct the subgroups. And we end up with this kind of MSE. It seems PC is quite good in this case. Okay, so the existing methods are also quite good. I'm not saying here that our method is always better than the existing method. You see, in some situations, the existing methods are also quite good. But I think the advantage of our method is that we can provide a model we can provide a statistical model to provide a better interpretation. We can actually say how these different subgroups are defined. We can talk about the subgroups. We can give a clear definition. Some of the existing methods, they couldn't even tell you how to write down the definition of different groups. They don't have models. So that's one thing that's really not that pleasant. Okay, so those are the main works I want to summarize. I want to share with you today. So finally, I just briefly mention what kind of future work I plan to do. So first, this model is very simple. It's still a parametric model. Clearly, a parametric model is too restrictive. Sometimes you may even consider a non-parametric model like a previous speaker. You can consider B-spline. You can consider all kinds of spline models as well. So definitely, it fits that kind of framework very well. You can try that kind of, we perhaps can do that kind of analysis as well. And also, causal inference is quite important, especially in computing technology. And so I'm also thinking that for observational studies, when you cannot have a golden standard, if you want to do some causal inference, you can also try to do this kind of subgroup analysis. Even so now I don't have a very clear idea of how to do that yet, but I seem to find that there is some connection over there. You may want to look into that. And finally, we are still developing the software, and we hope the R package will be ready soon, and then you can use the package directly to do all the calculation. So that's all. Thank you very much.
In your simulation, your model, right, your Z is generated kind of from like a factor analysis type.
Yes, yes.
It seems like, I guess, in Python Z probably is not known.
Yes,
so
yes.
I was wondering if you did any simulations where you get the Z wrong, you specify the Z, so maybe I don't know, if you use some related coverage or something that's not factor analysis based, and how your core methods for getting the Z work out on the model.
Yeah, we indeed have tried many situations. Because in this kind of subgroup method, we believe there is a true model. So in that true model, there is a true underlying factor, underlying latent variable there. So in the simulation, we just pretend we know. In this simulation I showed, I just pretend I know the true variables. I also have done some kind of analysis where we don't know. Yeah, we don't really know the true underlying variable may be misspecified. Okay. In those situations, what I can tell you is, so first, the number of groups, this seems to be still okay. If you use a factor or use PC to do that kind of approach, if the true variable is kind of parallel to those PC or factor variable, parallel means they are correlated. Okay, if they are correlated, then sometimes they can still identify pretty well. If they are completely unrelated, then it will be wrong. It will be very hard to do. Yeah. So yeah, that's a very good question. Yeah, we need to indeed worry about the misspecification. Yeah, it's important. Go ahead.
Eventually trying to do causal inference, or you're talking about maybe having one that can be like a treatment indicator?
Probably, and maybe even put the instrument variable somewhere in the model. So that's just a very rough idea. Even when I was writing these slides, I was suddenly think I can put this in. Since I'm in this workshop for so long, I heard you guys talking about this so much.
I was just curious, so you look at MSE.
Yeah.
How good are your estimates of
Beta, huh? Yeah, I didn't check for beta because there are quite many betas in the model, so I didn't check individually. Yeah, it could be related. If you can estimate beta well, then you can predict Y well. So usually that's a logic connection. But here we only check the final consequence. We only check the Y, and yeah, I think so. We can also check beta.
Right. Yeah, because I think in the causal, or they're trying to do some kind of
Mm. Yeah. Yes. Because in terms of beta, I think in our previous paper we already showed the regression coefficient. They can indeed be consistent. Well, as long as if your z is correctly specified, then we do have consistency for beta. Yeah. But this is new. Of course, this is new. We haven't done any thing on that yet. Mm. Beta J. Mm. Do you mean you want to make sure this term is significant? Yeah. Right. Mm. 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 Yes. Okay. So in order for these theoretical results to hold, we need some technical conditions. One of the technical conditions is this beta j plus 1 minus beta j must be non-zero. Okay. Otherwise, the change point is not different, is not identifiable. Okay. We must make sure there is a jump. If there is no jump, then it's not that there is no change point. So the condition is required. There must be a jump. So this is the model we believe exists. So we believe that the model must follow this kind of structure. Okay. If you in this model, in our procedure, we don't really know if there is change point, right? I also showed you some simulation results. When there is no subgroup, we can indeed find out there is no subgroup. We won't overestimate the number of change points. Yeah. So we indeed checked on that side. Yeah, we do need to worry about that. Yeah. Yes, some of the X can be continuous, can be categorical. You can incorporate them. Yes. Oh, you mean PCA? Oh, that's a good question. Because for PCA, it's usually only for continuous variable. Factor analysis is also only for continuous variable. So here we only consider continuous variable. For categorical variable, you cannot do this. Okay. You have to consider other ad hoc methods to incorporate them. Thank you.
So okay, we come back at 45. I'm not sure what the speaker will be by then. because we are running with arguments. Yeah. Maybe you can do another topic. You can talk for 2 hours. I'm 25, so you need to have 5.
I actually don't think
that was no, it's not in the so I know where it's shooting. So for that, is it the last figure? Is it the step? This one, last figure is also. Oh, wow. Even that is okay, I think that's that's another one. But it's not the theater is very, but